Hello, welcome back. Today we're going to look at partition equal subset sum. Tongue twister there. Given an array nums, return true if you can partition the array into two subsets such that the sum of the elements in both subsets is equal, or false otherwise. Okay, so example 1, nums is 1, 5, 11, 5. And that's true because the array can be partitioned as 1, 5, 5 and 11. Okay, so what does that mean? 1 plus 5 plus 11 plus 5 is 22, right? So if 22 is, let's just draw it here. So if 22 is the target, right? So let's say there's 1, 5, 11, 5. Oops. Right, and the sum equals 22, then we want to take this array and partition it in some way where one side sum is 11, right, and the other side sum is 11, right, and that would make it equal, right, whatever can sum up to 11 and then 11. Now, I guess one key insight here, more of an optimization, is to notice that 22 is even. Right, so you can imagine if this was if there was an extra 1 here and the sum was 23, then we'd have to get both sides to equal 11.5. And it doesn't say that these are, oh yeah, it does say that these are integers. So if this is actually not even and it's odd, then there's no way we can partition these integers to have a 0.5 on each side, right? We'd have to have 11 here, 1, 5, 1 here, and then take this one, split it into a 0.5, split this into a 0.5, and then put a 0.5 here and a 0.5 here, right? So kind of an optimization, but if we see that the sum is odd, then we can't do this at all, right? So that's one thing to note. But let's say that we get this, right? And we see that it's even, right? So the sum is 22, and we want to split 11 and 11. So what we do know is that if we can get any subset of this one, this one, this one, this one, these three, or these two and this three, or this one and these two, or this one and this one, or this one alone, right? This one has an 11 just by itself. If we can get any sum of these, then we know that the rest of them could be the other partition, right? So if this was partition green, we know that the rest of the elements can be partition red. So we just want to find one single sum, right? In all of these subsets, we just want to find one single sum, right? So let's review what the subsets are, because the subsets are actually similar in many problems, right? So let me get my straight lines that I prepared for this problem, because straight lines are hard, and let's review what subsets are. How are subsets created typically in code? Well, we start off with something that's essentially an empty value, right? We don't take any of these values, right? With none of these values, well, the sum becomes 0, right? So the first subset is we take none of the values. Now let's take one of the values, right? So which value should we take? Let's just go down the list. We're going to make a copy of everything that we've already created. We've created nothing, just this 0 here. And we're going to take one of the values. We're going to take this 1, right? Move this up a little bit. We're going to take the 1, right? So now this is the 0 plus a single 1, right? And that's a 1. Okay, so we're done taking the 1. I'll put an arrow here if you get confused which one we're working through. Make that gold so it's easy to see. I'm going to move this, give it some spacing. Okay, so we've taken the 1, and now we want to go and take the 5. Now what does this entail? It entails copying everything that we had so far, right? And and making sure that we check off the 5 here, and each one of these sums has a plus 5, right? So these are all the subsets where there is a, for that one. Let's go to the 11. The 11 means that we still copy everything, right? Copy everything. And then in this case, we actually check off all the 11s, and we add an 11 to everything, right? And then let's continue the pattern, have the 5. And we add a 5 to everything. Okay, so these are actually all the subsets. You can try to verify it by looking at it. So these are all the booleans of does this one exist and does the other one exist, right? So let's just try to find one, for example. Let's imagine we want to take every value. Does every value exist somewhere here? Let's look. Make it green. Yeah, every value exists right here, right? What about the first 3 values? The first 3 values exist over here. What about the second 3 values? The last 3 values are right here. The first 2 values are right here. Second 2 values are here. Third 2 values are here. We have, just this one and just this one and just this one and just this one as well. Okay, so this is how you get all the subsets. Hopefully the demonstration was enough, but you start with a 0. You go through your list, and you essentially copy over the list, and then also add that value. And at the end of it, all of these are all the subsets of these 4 values, right? And we can continue on. If you added another value, an 8 here, we would do the same thing, right? We'd make a copy, we add 8 to it. And that's how you calculate the subsets. All right, so this is it's a similar problem to subsets for arrays, right? Like if this was an array problem, these are all elements of the array, then instead of summing these the way that we are, that these would just be elements of the array, right? So this one would be an array of 1, 5, 11, right? We would ignore the 0 actually. And this last one would be an array of everything, 1, 5, 11, and 5, right? It's just that the only difference between this problem is that we're summing them, okay? Creating the subset is the same across all of these problems, or many of them, maybe not all of them. So let's think through how to do it, right? So can we partition it? Let's think about that optimization. What is the sum of nums, right? Let's just put nums, the sum here. If the sum of nums is odd, right? So if it's not equal to 0, if it's odd, then we actually just want to return out of here. And what is it? We just return false, right? We return false. Okay, so what's our target? Our target is sum of nums divided by 2, right? Perfect. And we're going to create a some table for us to store these in some way, right? Or I guess we don't really need a table. We can just create a I'm going to call this DP, because technically I guess this is dynamic programming. I'm going to call this our DP, and I guess that could just be a set. It's just a set of all the numbers, right? And we're going to start at 0. Okay, so for all the numbers, right, for I in range and nums, we're going to do that operation. So what is this operation that we're doing where so we have to copy and copy, right? So this is going to be like our new DP, or our copy, right? And then we're going to populate the new DP, and then we're going to set DP DP as new DP, and really, if we ever see the target, we could just return true, actually, right? So here, if we never see the target, we've never seen the target, we can return false. Now that I think about it, I don't think we need this new DP. I guess we could just add to the DP, right? So we could just populate it. I mean, it's the way that we have here in the drawing. We're not creating a new DP, we're just populating it. Okay, perfect. So, well, how do we want to do this? I want to make a copy of this DP. Okay, so what I'm thinking is, do we make the copy here first? Do we copy this set? Or do we iterate over it? Because so if we iterate over it and we add to the DP, then the DP is changing as we're using it. And that's really not what we want. Right, so I'm going to keep this DP and then maybe we can refactor later. So let's add everything, right? So for num and nums, right, the actual num is here at I, and then we're going to populate it, right? So we're going to iterate through DP, so it's going to be like a existing value, right? Existing in DP, then the new DP, let's add that existing, let's just make sure it's there, and then let's add the existing plus the current num, right? And then let's set it to the new DP, and let's actually say if this is the new value. If the new value equals the target, right, we can actually return out of this entire function and return true. We don't need to continue iterating over this. So at any point, if we find this, actually, we could just return true. Set this as a new DP. Move this comment up here. And if we never find the target, I guess we could just return false. But we've never found the target. So let's look through the code and see if it's doing what we're expecting, right? So we start the set and it's going to be starting at 0. Okay, perfect. We're going to create a new set. We're going to take one of the values, 1, and we're going to add both that 0 and that 0 plus 1 to the new set. Okay, so the set is no longer that. The set is now this, right? Perfect. Now we move on to the next number. We move on to number 5. Now number 5, we're going to add all of the existing, plus we're going to add all of them while adding the 5, right? So now it's this one, right? So it's expanded, right? We look at the 11. 11 is the same thing. We add all of the ones that are existing, and then we add the 11. And then for the 5, we add all the ones that are existing, and then for each one of those, we add the 5, right? This is our new set. If at any point we found our target, like here we found it at 11 actually, right? Then we can actually just return true. Otherwise, we add that new value to the DP, we continue on as normal. So, you know, the confusion that I was thinking about in the beginning was, do we need this new set operation? Can we iterate over this as kind of a snapshot in time? We cannot, and that's fine. We don't need to. So let's run this. Let's see if their syntax is invalid syntax. Okay. So for I in range. For I 4 needs to be 4 in. Okay, so we got those. Let's run this and great. So we got decent runtime, 230. You know, takes longer than our other problems. But what's important is that we understand this from the components that make up the problem, because you're probably not going to get this exact problem in an interview. It could be some variation of it, right? So the optimization, not as important because it doesn't help us solve it, right? You could actually get rid of the optimization. I wonder how long this would take. Oh, you actually can't get rid of the optimization because you're going to run this. Yeah, you actually can't get rid of the optimization because you're going to run it and something's going to be missing. What's going to be missing here? So this is going to be 11, and the output's true because, oh right, because you can sum up to 11. Oh right, so yeah, so you don't want to get rid of the optimization. You want to keep it. But yeah, so the components are the optimization, and then to be able to do the DP on subsets, where subsets are basically this pattern, right? This pattern where you're creating this table, you're copying it over again, you're copying it over again. One thing that I'm thinking about is I can actually delete the optimization. The problem that I had is that I'm returning on this target found, and the issue is this is a partition problem, right? So you might get some subtle variation in a real interview where the partition means that if I use every value to add it up, then it's not a partition. So technically this is not a partition where I'm using every value, right? So you know, there's nothing here that says, hey, if you use every value, don't return true. So it could be something to think about in a variation of this problem where it's not an equal subset sum, it's maybe some different type of target subset sum, right? Anyway, the main parts are this diagram here, and hopefully you get that as well, right? And that's going to be a super similar problem. If you see the word subset, it's going to kind of, it should give you a hint that this is going to be an approach. Let's just search subset. Right, so, oh, here it is. So subsets is going to be one of the upcoming problems, and this one's going to be essentially the same problem, right? This one's going to be subsets, but it's an array, and you know, the solution is almost the same algorithm. You start with results, but here you start with an empty array, and then you make a copy, you append to it, right? And this copy is you know, you iterate over that, append to, and then you append the result. I guess this one's a little bit different, and maybe I can take the learning from this one. So here we're taking a copy. So, you know, just to read the problem: subsets given integer nums of unique elements return all possible subsets. The power set solution must not contain duplicate subsets. Return the solution in any order. If you see this here, these are guaranteed to be unique, so that's actually a massive difference. And you know, it's actually much easier because they're guaranteed to be unique, where we're just appending the sum to here based on the copy. So if we wanted to copy that exact solution, could we do it? Let's think about it. The way we would do it is you'd imagine a results array here. Let's just comment this out. You'd imagine that the results array here. Then for I in range nums, you take a copy of results. So let's say results had just a 0. You'd say add to results copy, and then for result in, or what do I call it here? For result and add to, then result we're going to append add to and nums at I, right? So at the end of this one, so what we want to print here is all the subsets, right? So this is all the subsets. This is actually what we've computed in the diagram, right? We have 0, 1, 5, 6, 11, 12. And if you actually add these numbers up, you'll get it, right? So this should be 0, this should be 1, this should be 5, this should be 6, 11, 12, 16, so on, right? And that's exactly what we have here because we're getting we're doing the same thing. We're just doing it in code, right? So actually at this point, right, we can do the same thing where target can be equal to this, right? And target, well, let's call it value, right? If value equals target, then we can return true out of this function. Let's print results anyway and return false. Right, so here, return true, return false. Now, I wonder if we run into the same problem. I'm going to submit it, where we're using the entire length of, I see. So the memory limit exceeded because I guess because I'm doing the copy, and I'm doing the copy again. I guess this is not really, let's think about it. Why would the memory limit be exceeded? Is this less efficient than this? Doesn't seem less efficient, right? The only thing I can think of is that this is not a set. If this was a set, could you is this any more optimized because it's a set? Interesting. Okay, so roughly the same runtime actually, and I don't remember if it's the same memory. Let's see. So the memory is 17, and before it's actually the same exact runtime and almost the same memory. So I guess these are two solutions to the same problem, and it's quite honestly the same solution, right? So we have some result set. Well, we make a copy of it. But here I'm starting it empty first, and then I'm appending to it. Here I'm just making the full copy, right? And then I'm appending to this. I'm making the full copy, and then I'm appending to this source array, or this source set. So roughly the same problem. I'm surprised it uses the same memory. So this is going to be, I guess subset problems are n squared operations, right, to create all these subsets. Or is it n factorial? Right, so it's 1 times 2. No, it's this times this times this times this. I think it might be 2 to the n. I'm not sure. I'll have to check on that. Maybe you can ask LeetCode. It might be to the n because for every one of these it's doubling. So it's a doubling for however large n is, right? So if I had nums is a super large number, I wish I could see their test cases, then it's going to be pretty large. Anyway, thanks for visiting. You know, I wonder if this crashes it. So let's just add some numbers here. And I wonder if it could even run this. If it's truly to the end, it should not. It's not a valid value of type integer. I see that right there. Run that. Nums must consist of 1 to 100 only. Okay. So let's delete this and let's delete that. I have a 300 here, so let's make that a 2. Let's delete these. And let's delete this. Okay, let's see if it can run this. It can. All right. Thanks for putting up with that one. I'll see you in the next problem. We're going to keep going. Let's just check this one off. String to integer. That looks interesting. We'll see you on the other side.